Imagine a single object, cold, precise, and patient, falling through the sky with the intent of burrowing into stone and steel. This is the story of the GBU-57, the Massive Ordnance Penetrator. A weapon built not for blast radius or spectacle, but for quiet, inexorable force. We begin not with thunder, but with geometry and weight. At roughly 20.5 feet long and just over 2.5 feet in diameter, the GBU-57 could be mistaken, at first glance, for another strategic munition. Its silhouette is familiar, streamlined, purposeful. Yet within that familiar shape lies a different kind of power. Where a cruise missile carries speed and guidance for distant targets, this munition carries mass. Nearly 30,000 pounds of concentrated force, designed to translate momentum into penetration. More than 5,000 pounds of that mass are explosive, carefully chosen and arranged to do maximum damage after the weapon has already broken through. Guidance is not left to chance. The GBU-57 wears a KMU 6-on-12 tail kit, a navigation brain borrowed from the family of GPS-guided munitions the United States has perfected over decades. When the weapon is released, 4 lattice fins unfold like a living mechanism, each moved by its own actuator. They do not make the bomb graceful, they make it accurate. The trajectory is small, the margin for error slimmer still. It is a fusion of brute physics and surgical precision. Beneath the case, the BLU-127 warhead sleeps, a composition of explosives engineered for a single, ruthless purpose. AFX-757, the primary charge, behaves more like a highly energetic propellant than a conventional explosive, optimized to convert the bomb's immense kinetic energy into shock and cavity behind hardened barriers. Complementing it is PBXN-114, a supporting formulation that shapes timing and effect. Together, they turn penetration into destruction at the precise moment the weapon finds its mark. And yet, even as the GBU-57 stands as the largest and most powerful bunker-busting munition in history, the story continues. The Department of the Air Force has awarded a contract for its successor, a Next Generation Penetrator, signaling that the task of breaching the most protected shelters is an evolving problem, ever inviting new solutions. This is not a tale of intimidation alone. It is an account of engineering and intent, of physics harnessed to policy, of technology that moves forward in quiet increments. As we watch the arc of design and procurement, we are watching how nations choose, in the hush before impact, to translate planning into power. What surprises you more? The thunder of an explosion, or the patient wait that makes the thunder possible? Inside the 30,000-pound hush of the MOP, the blast is a small part of the story. The explosives, the part you might imagine as the whole, account for only about 1/5 of the weapon S mass. The rest is a monument to hardness, a dense armored body engineered to chew through earth and concrete long before the charge ever sings. With no engines, no fuel tanks, no flamboyant propulsion system, the weapon's violence is borrowed from gravity and delivered through sheer mass. More than 20,000 pounds of steel and structure carry that intent, so thick and tough in places they measure more than 3 inches. A shell made to be a drill more than a casing. Those casings are not the product of a single machine shop. They are the work of heavy industry. Forged and finished by firms like Superior Forge and Steel in Lima, Ohio, and Elwood National Forge in Irvine, Pennsylvania. These components were built to tolerances and strengths most machines never see. Work that carried a price tag measured in the tens of millions. The result is a blunt instrument refined by metallurgy, heat, and craft. A body that converts falling speed into the ability to breach the most stubborn shelters. And yet, the story does not end with weight and metal. The next chapter is being written by different hands. Applied research associates will lead design and manufacture of first subscale and then full-size prototypes, while Boeing focuses on the new guidance section and the tail kit that will let the weapon find its mark. Together, they are building not just a bigger hammer, but a smarter one. A system intended to navigate when the sky itself stops whispering coordinates. That matters because the new penetrator is supposed to be precise in places where GPS is uncertain or absent. In current footage of the MOP and testing, accuracy reads almost clinical. From tens of thousands of feet, dropped from a stealth bomber, the weapon can fall onto a single traffic cone, marking a point on the ground. It is a startling image. A massive, quiet object finding a tiny target. And it speaks to the convergence of brute force and delicate control. The future of these weapons is not simply about making more destructive tools. It is about making destructive tools that can still be guided when the signals we rely on are gone. So we watch both the steel and the silicon evolve. We watch the slow arithmetic of weight and the rapid calculus of guidance intersect. In that intersection lies the uneasy magic of the bunker buster, an apparatus that asks the world to hold still for a single decisive moment and then delivers everything it carries, mass metallurgy and mechanized intent, into that pause. What happens when the balance between mass and mission is suddenly asked to change? By design, the Air Force has told us something precise. They want the new warhead to weigh less than 22,000 pounds. That number is a promise and a constraint, an invited puzzle for engineers who must squeeze the power of the MOP into a lighter, smarter package. Yet beyond that warhead figure, the full weight of the Next Generation Penetrator remains a quiet unknown, a question mark hanging on procurement spreadsheets and in the minds of the men and women drafting blueprints. Today, the GBU-57 lives under the wing of a very particular aircraft, the B-2 Spirit. Its dimensions and mass were matched to that airplane's limits and privileges. The coming NGP, however, will most likely ride a new bird, the slightly smaller B-21 Raider. That swap alone reshuffles the problem. Fewer inches of clearance, different load bay geometry, new structural limits, all of it forces designers to reconsider how much brute weight is feasible and how much must be traded for other capabilities. Trade-offs are the heartbeat of weapons design. One obvious path forward is paradoxical: increase penetration while shedding pounds. Engineers might seek materials that are lighter, yet stronger structures that act like drills rather than blocks of steel, or even add propulsion, a whisper of thrust that could give the weapon speed and control after release, letting it dig deeper without relying purely on falling mass. Propulsion would change the equation entirely. The penetrator would no longer be a passive hammer, but an active instrument, able to shepherd its kinetic energy into the ground with intent. And yet, the record is messy. Official facts and operational realities sometimes tell different stories. For example, official B-2 documentation states the bomber should carry a single GBU-57. In practice, reports from recent operations suggest that some aircraft were loaded with two. When lives, targets, and national decisions hinge on numbers, those discrepancies matter. And they remind us that secrecy, improvisation, and battlefield necessity often blur the tidy lines of manuals and fact sheets. In other words, some of what we read must be taken as provisional, shaped by policy, practice, and the fog that hangs over the most sensitive missions. Regardless of the numbers or the theories, timelines compress and expectations harden. The Air Force intends to move quickly. Full-scale prototypes of the new bunker buster are slated for testing within the next 2 years. Those tests will be a crucible, where design choices meet reality, where metallurgy, guidance, and the possible inclusion of propulsion will be tested not on paper, but in measured, dramatic detonation and impact. So we stand watching a quiet transformation unfold. Will the new penetrator be lighter and smarter? A surgical tool that finds its way through denied skies and buried fortresses? Or will it remain a monument to mass, refined but familiar, the successor merely reshaped from the same intent? The answer will be written in steel, soot, and data. In the way a prototype falls, the way a payload survives impact, and the way engineers then go back to the drawing board. For now, the future is both constrained by physics and opened by imagination. Between the figures on a fact sheet and the echo of tests to come, nations prepare for a question that will soon be answered not by words, but by impact.